So as we probably all know, one of the main questions in symplectic topology is, as with any kind of topology, is to classify. So let's just set up our notation. I'm going to be mostly talking about subsets of R2n with a standard symplectic structure. And the most basic question is, given two subsets, when is there a diffeomorphism that preserves the symplectic form? So that's what we call the symplectomorphism. And the question two, which is a bit easier, is when does there exist a symplectic embedding? So those two questions are going to motivate everything that I'll talk about here. And I think we all study probably these questions from one angle or another. So let's start with the symplectic embedding question. So I think also we all know that the nth power of the symplectic form is the volume form in R2n up to a factor, which means that if you preserve the symplectic form, then you preserve the volume form. Now we can talk about the basic question that Gromov looked at in the 80s, which is, given a ball and a cylinder, when can you embed the ball into the cylinder? And I think, again, most of us here are probably familiar with Gromov's non-squeezing result, which is that you can only embed the ball into the cylinder symplectically if the radius of the ball is at most the radius of the cylinder. So you can also think about this in terms of symplectic shadows. And just a little caveat, which I think is always helpful to remember, is that this problem is very sensitive. So if you look at a different cylinder, for example, if instead of restricting Q1 and P1 to be in a disk, if you make Q1 and Q2 to be in a disk, then you have no more rigidity. Basically, now you can do anything you want. So that's because the symplectic form pairs. So this just is the very beginning of people's understanding that symplectic rigidity and flexibility are very subtle things, and you can jump from rigidity to flexibility really quickly. Okay, so one way to encapsulate or to try to understand the symplectic embeddings is by using what's called the symplectic capacity, which is, I think, a term that was first used by Eklund and Hofer shortly after Gromov's result. So symplectic capacity is a function that will assign a number, a positive number or infinity, to a subset of R2n, or maybe to a symplectic manifold if we're in another kind of category, with the following properties. So it scales with R squared when you multiply your set by R. So it's a two-dimensional invariant, even in higher dimensions, which is so you can also think about that it scales with the symplectic form if you scale the symplectic form instead. The second property is the monotonicity. So it obstructs symplectic embeddings. So whenever you embed one manifold into another, the capacity will not decrease. And finally, a non-triviality condition, which is that the ball has positive capacity and the cylinder has non-infinite capacity. So in particular, this capacity cannot be really related to the volume, cannot really be an exponent of the volume to some power that would violate this last condition here. And it can't be identically zero. Okay, and we say that capacity is normalized if the capacity of the ball and the cylinder are the same. Okay, so then we usually take that to be pi r squared just for tradition. And one interesting comment is that the existence of a normalized symplectic capacity is equivalent to Gromov's non-squeezing theorem. So this is a simple exercise, but if you haven't seen this before, I think it's worth thinking about this little fact. Okay, any questions? Okay, so the simplest capacities are what's called the Gromov width. So that's the biggest ball, the biggest pi r squared of the biggest ball that you can embed into your X. And another very simple example is doing the opposite for the cylinder. So the smallest pi r squared such that X embeds into your cylinder. And it's another easy exercise to see that if C is a normalized capacity, then it is in between these two. Okay. Here are some other examples of normalized capacities, which you might have heard of before. So there's the first Ecklenhofer capacity, which is the first, I think, capacity that had that name. And then Hofer and Zender, in their book, defined the Hofer-Zender capacity, which is a bit easier to define than the Ecklenhofer capacities, but using kind of similar variational methods without holomorphic curves. And then there's the Floer-Hofer capacity, which came out in '94, which uses symplectic homology. And then much later, Gut and Hutchings defined capacities using positive S1 equivariant symplectic homology, which we call contact homology. So the first one is normalized. And in dimension 4, there are the embedded contact homology capacities. And there are other capacities, but these are just some examples of normalized capacities. Okay, so let's talk about the Viterbo conjecture, which is a conjecture about capacities. So one very simple exercise, again, I've given you lots of little exercises for the students and for those who are bored. So is to see that for the Gromov width, there is a simple inequality for any compact set. So that the Gromov width to the n over n factorial is less than or equal to the volume. Okay. And the proof is very simple. It basically just uses the fact that if you have a symplectic embedding, then it preserves the volume form, so it preserves the total volume. And all you need to know is what the volume of the ball is. So that's just the Gromov width of the ball to the nth over n factorial. So that's why we have this. Yeah, so here it is. Okay, so then Viterbo, looking at some examples, he conjectured the following thing. He knows this can't be true for every set and for every capacity, but he conjectured that for convex sets, this inequality always holds for a normalized capacity. So that's the Viterbo conjecture, that for a normalized capacity and a convex set, we have the same inequality. And moreover, we only have the equality if X or the interior of X is symplectomorphic to a ball. Okay, and I think many people here have heard of this conjecture, and I want to say that the state of art, I think, is that it's still pretty widely open, and I think even dimension bigger than 4, I'm not even sure that there's that much evidence for it, but it probably, I mean, I still think it probably should be true, but I think it's, I don't know how much we really believe it's true. Yeah. Okay. Any questions about the conjecture or what I've said so far? Okay, so I want to now talk about a weaker version of this conjecture, which is the following. So if you have a compact and convex set with smooth boundary, you can look at the shortest period of a closed wave orbit on the boundary of X. That's also called the symplectic action of the closed characteristic. So we know there always exists one. I think by Rabinovitz, the most primitive version of the Weinstein conjecture. So you can look at the smallest symplectic action or the smallest period of a wave orbit. And a bunch of people proved that different of these capacities coincide with this minimum action. So I guess the first result, like by Ecklenhofer / Hofer and Zender, they showed that the first Ecklenhofer capacity it coincides with this minimum action for convex sets, and a few other ones. So we can ask a weaker version of the Viterbo conjecture, which is basically just the Viterbo conjecture for the minimum action. So if X is a compact and convex set with smooth boundary, then we just want the Hofer-Zender capacity or the minimum action to have this inequality, to satisfy this inequality. And moreover, the equality holds if and only if the interior of X is symplectomorphic to a ball. And this conjecture is still open. So even though it's just for one capacity, it's still open. But I want to now quickly tell you one reason why this conjecture is interesting. Okay, so it has to do with the Mahler conjecture. I mean, that's one of many reasons why this conjecture is interesting. So what's the Mahler conjecture? So consider another convex set, but now in Rn, not in R2n, so in any dimension basically, which is origin symmetric. That means that minus k is equal to k. Okay, so if you have a set like this, you can look at its polar body. So the polar body is the set of points whose inner product with everything in y is less than or equal to 1. And another way to think of it is you can think of K, if it's a compact convex set that's origin symmetric, you can think of K as the unit ball of some norm. So K defines a norm. And K and the polar body is the unit ball of the dual norm. Okay. So Mahler in 1939 conjectured that basically the following thing, that the volume of K times the volume of the polar body has a lower bound. And the reason he conjectured this is because he proved that he managed to prove that in dimension 2, but not in higher dimensions. And he in the conjecture is basically that this equality is attained for the hypercube. So if you take the interval to the nth, that is when you get this number 4 to the n over n factorial, you attain that number for the hypercube. So it's not hard to attain that number. Or to come up with that number if you believe the hypercube minimizes this product. Okay. All right. So let me just tell you. So the hypercube are not the hypercubes are not the only minimizers of this product. So the other set of minimizers, or a wider set that includes the hypercubes, are what are called the Hahner polytopes. So the Hahner polytopes are basically the following thing. So instead of just taking the interval and taking the Cartesian product with it multiple times, you allow to basically at some point you can take the polar body. So you take the set generated by the interval and the operations of taking the products and taking polar bodies. Okay, so this is a much bigger family in higher dimensions. So here's an example. This is an octahedron. Which is the dual of the three-dimensional cube times an interval. And this is a projection to R3, or I guess to R2. And it's an interesting exercise to see that for any Hahner polytope, this Mahler product, this Mahler volume, the product of the volume of K and K dual, is still 4 to the n over n factorial. So the conjecture that's still open is that this Mahler product is minimized, Mahler volume is minimized precisely by the Hahner polytopes. So there's nothing else. Okay, so why am I talking about the Mahler conjecture here? I'm talking about it because it's related to the Viterbo conjecture by this very beautiful result by Artstein-Avidan, and Ostrover. So in 2014, they showed that the weak Viterbo conjecture, so the Viterbo conjecture just for the minimum action, implies the Mahler conjecture. Okay, so we have that the Viterbo conjecture implies the weak Viterbo conjecture, and that implies the Mahler conjecture. And there's another conjecture here that sometimes is known as the strong Viterbo conjecture, but it was actually independently posed in the early 90s, which is that all normalized capacities coincide. So that would be the strongest one of all. But I'm not going to talk about it today any further because it won't be relevant for me. But it's still actually a possibility that for all convex sets, all normalized capacities coincide. And if that's true, then we have Viterbo and we have weak Viterbo and we have Mahler. Okay, so their proof is quite intertwined with what I'm going to say later. So I'm going to mention a few steps for the proof of this theorem. So it involves looking at what are called Lagrangian products. So a Lagrangian product for me, and sometimes I'll write a little L under the Cartesian product. Sometimes I'll forget, but actually all products pretty much that I have for the rest of the talk will be Lagrangian products. So Lagrangian product is a product of this form. So you take two sets in Rn and you look at their product in R2n. And by Lagrangian, I really mean like the way that you embed this product into R2n, which will be like this. You take the Q coordinates in K and the P coordinates in T. Okay, so that means that the two factors K and T correspond to Lagrangian submanifolds. So if you fix any value of P, then K times that P is a Lagrangian submanifold. And if you fix any value of Q, Q times T is a Lagrangian submanifold. That's why it's called a Lagrangian product. And one of the interesting things about Lagrangian products, first of all, they give you a lot of examples of interesting subsets of R2N. But one very interesting thing about them is what happens with the characteristic flow on the boundary. So the rate flow on this boundary. So let's analyze what happens. So if you've seen this before, I apologize for doing this again, but I think some of you haven't seen this picture before. So it's actually very, very beautiful. So how do we find the characteristic flow or the rate flow on the boundary? One way is you can look at the boundary of your subset as the level set of some Hamiltonian. So in this case, my Hamiltonian is not smooth. So, it's not ideal, but let's overlook that and see what happens anyway. So, I can think of it. I'm assuming K and T are origin symmetric to make it simpler. So that means that they give rise to norms. But you can even do that when they are not centrally symmetric. But let's just suppose that for this slide, for this calculation. So the boundary will be the pre-image of 1, where H is this function here, the maximum of the two norms. And of course, the boundary here, it's a manifold with corners. So the boundary is not a smooth manifold, but we can think of it as having two smooth parts. So we have K times the boundary of T and T times the boundary of K. So basically the Hamiltonian vector field is just minus J times the gradient, and it will basically have two expressions. It's not a smooth vector field, it's not even continuous, but it's still a vector field in these two parts. So it's given like this. So you take the normal vector so on Q times the boundary of T, you take the normal vector to P, but now you take the coordinates in the DDQI plane. So basically, that's what happens when you multiply by minus J. And on the other part, you have the normal vector to Q, but then you look at this vector in T, basically, with a minus sign. Okay, so that's what the characteristic, that's what the Hamiltonian vector field of H is. So we can draw the diagram. So, this is not really the boundary of Q times T, it's just a representation of it. So if you're in the boundary of Q times T, you're either anywhere in K and on the boundary of T, or you're anywhere in T and on the boundary of K. Okay, so let's suppose that I start with a point like this. So I start with a point on the boundary of T and somewhere in K. So if I flow by my vector field XH, then I have to look at the normal to P here, and then I have to flow Q in that direction. So this is what happens. And then until I hit the boundary of K. So when I hit the boundary of K, there's this corner of my manifold. And then, something happens on this corner, and I'm just gonna ignore the fact that it's not non-smooth. And then from then on, I'm gonna just go into the other part of the manifold. So now basically I'm gonna go into the second part, and I'm gonna follow this other vector field. So now I have to follow the vector field that is in the direction of the normal to Q, but I have to move P in that direction with a minus sign. So this is what happens. Okay, so this is this direction is minus the normal to Q. And then I keep going. Now I go back to K times the boundary of T. So I have this. And you can notice that the blue angles and the red angles coincide. And you can keep going. And basically what you see is that the Hamiltonian flow you can think of it as two different trajectories, which are billiard-like. So there are two billiard-like trajectories, one in K and one in T. And I say billiard-like because these are usually not, this is not going to be the standard reflection. But you see that the reflection here on the K side will be given by the reflection law can be understood in terms of the geometry of T. And vice versa, like if you keep looking at this trajectory in T, the bouncing here will be determined by the geometry of K. So these are kind of intertwined, generalized billiard trajectories. Okay, so that's one reason why Lagrangian products are so interesting. In particular, if K and T are the disk, then these will be two billiard trajectories on a disk, like standard Euclidean billiard trajectories on a disk. Okay, so now that this hopefully makes sense to you, we can quickly show the idea of Artstein-Avidan and Ostrover's theorem. So suppose that we take an origin symmetric compact and convex set in Rn. Then the main thing they proved is that the Hofer-Zender capacity, so the minimum action, is always equal to 4, no matter what K is. And the idea is just this picture. If you take K and you take the polar body, there always exists two trajectories, billiard trajectories, one in each, that are intertwined, that go like this, go boom, 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 boom. And it's a simple calculation that this always has action 4. Okay, so that's kind of, that picture is the proof of their theorem. So now you just just plug it in. So this Hofer-Zender capacity, its minimum action is always 4, so you plug it in like that. By the Viterbo conjecture, this is less than or equal to the product, to the volume of the manifold of the subset, and that's equal to the product of the two volumes. Okay, any questions about this? Okay, so, all right.
There's a question in the chat.
Oh, is something known about the Gromov width of the product? Yes. So I think it is not known in general if the Gromov width is always 4. I mean, the Gromov width is at most 4. And definitely for many examples, it is known to be 4. Like, I mean, yeah, so definitely like for the product of two balls, so if K is a disk, sorry. If K, yeah, so in dimension 2 at least, if K is a disk, then the polar body is also a disk, and it's known the Gromov width is 4. So basically, the question is, can you embed a ball of symplectic radius 4 into this K times K dual? And it's definitely true for the disk in dimension 2. It's also true for the hypercube. K is a hypercube. And I am not sure if it is known in general. I think Johan is here. Maybe he knows. Yeah, I don't think it's true in general. I don't think it's. I'm not sure if it's.
I mean,
known.
the fact that the Hofer-Zender capacity is a normalist capacity will tell you that you can always embed a ball, but maybe you can. Oh no, maybe no. Yes, the problem is like you need to show that you can embed a ball, and you're saying this is a ball of radius of capacity, sorry, 4.
Yeah.
And you're saying this is known for examples, but you can't kind of extract it from the geometry in general or something.
I don't think it's no. Yeah.
So sorry, is it sufficient that you have embedding of a ball of capacity 4 to know the Gromov width?
Yes, it is, because we know that the Hofer-Zender capacity is equal to 4. So the Gromov width cannot be bigger than 4.
Okay, thanks.
Yeah. Yeah, so I think, in general, it's not known. And I should say, like actually getting the Gromov width to coincide with the minimum action is pretty hard to do. There's some recent work by Oliver Ettmeyer where he shows that for convex sets, there's a capacity which is not quite the Hofer-Zender capacity, but it's basically the first ECH capacity, which we don't know that coincides, but it's a capacity that comes from actions of ray orbits, and he shows that one coincides with the cylindrical capacity, which is the biggest one. So that gap he filled. We still have, a little work to do between like C1 ECH and C1 CH, but the gap between sort of capacities that are actions of ray orbits and the Gromov width seems to be pretty big. Although I don't know, maybe someone tomorrow will show that they coincide.
I think the answer is in the chat by Yaron.
If one can prove the Gromov width is 4, then you get Mahler's conjecture. Yeah. That's true because we already know that the Gromov width, that the Viterbo conjecture is true for the Gromov width. By the, it's just a simple calculation like I told you a few slides ago. Thanks, Johan. Okay. All right, so let's continue. So now I want to tell you about some of the equality cases in Viterbo's conjecture. So one thing that you can easily see is, as I told you, is for the hypercube. Actually, this is a slightly different calculation, but it's basically the same. That if you look at the hypercube times its dual, so that's the unit ball in the L infinity norm times the unit ball in the L1 norm, that satisfies the equality of Viterbo's conjecture. It's basically the same calculation that for k equals in that satisfies equality in Mahler's conjecture. And more generally for a Hunter polytope, the product of k and the polar of k also does. So in 2019, Daniela Sepe and I proved that that this configuration is symplectomorphic to a ball. And I should say that it was known before for a long time, since at least Schlenk's book, so since his thesis, that this product is symplectically equivalent to a ball. And it was also known that for n equals 2, that it's symplectomorphic to a ball, although in the mention for n equals 2, basically 2n equals 4, and a lot of things, we have a lot more methods. So using McDuff's isotopy of ball embeddings, you can construct a symplectomorphism in dimension 2 a long time before our result. But our result is good in any dimension. And in a way, it's much simpler. It doesn't use holomorphic curves, as I'll explain in a little bit. So it's still an open conjecture whether this is true for a Hunter polytope. Although I think it is probably true. We can probably modify this theorem, but I haven't been able to work out the details yet. So now for the rest of the talk, I want to talk about a family of products that have to do with a slightly different configuration. So you can notice if you just do an example calculation with billiards, that if you take the product of the equilateral triangle and the regular hexagon, that also satisfies equality in Viterbo's conjecture. So now you're wondering, so is this symplectomorphic to a ball or not? And that was the question that Johan asked me a few years ago. And it turns out that the answer is yes. So in fact, we can prove that this product is a ball, in a 4-ball, and we can prove that a family, something similar to this result with Sepe, which is that we have that a similar thing holds in every dimension. So let me explain what the generalization would be of the triangle and the hexagon. So the generalization of the triangle is, it's easy to imagine what kind of object it is, at least topologically. So this will be a simplex, this delta n. And here it's a specific simplex. So it's not actually a regular simplex in general, but it's a simplex given by these equations. So you look at Rn plus 1, and you look at this hyperplane in Rn plus 1, where the difference of, and then you look at the difference of the 2 consecutive coordinates is less than 1. And you look at this cyclically. So that means like the last coordinate minus the first coordinate is also less than 1. And here's another set that I'm calling Rn. So this is a set of points in Rn plus 1, also in the same hyperplane. But now I require that the largest coordinate minus the smallest coordinate is less than 1. Okay. So a simple exercise is that in dimension 2, this delta 2 is just actually it's the equilateral triangle, and R2 is the regular hexagon. Okay, so that's another exercise if you're bored. So what we proved this year, and the paper is going to be on the archive very soon, is that the product of this simplex and this polytope Rn is always symplectomorphic to a ball. Okay. And I should emphasize here that we have strict inequalities here. So we have the open sets, and the ball here is the open ball. So we're not going all the way to the boundary. There's no hope. I mean, of course, going to the boundary because the ball has a smooth boundary, and this Lagrangian product has a boundary with, with corners. So here's an example. I mean, here's a picture of the n equals 3 polytopes. So we have the 3 simplex, and this thing is called a rhombic dodecahedron. So this is one of the generalizations of the hexagon in dimension 3. So these Rn are basically, these Rns are a generalization of the regular hexagon. Some people call it the generalized rhombic dodecahedron, but I think this name is not that standard. So I'll just call it Rn here. Okay, any questions about this? This is the main theorem that I wanted to present. Okay, so now let me tell you about related results and like wider results. So to do that, let me remind you of what a toric domain is. So a toric domain is just a set in Cn that is of the form mu inverse of omega, where mu is the standard moment map and omega is some open set in the first orthant of Rn. Another way to think of it is you take some set in Cn, which is preserved by the standard Hamiltonian toric action. And this omega is just the image of the moment map. Okay, so, examples are a cylinder, and here's an ellipsoid. So now let me tell you how this is related to what we had before. I mean, of course, a ball is an example of an ellipsoid, is a toric domain, so it's not surprising that toric domains are coming here. So we can actually prove a lot more than what I just stated for the rhombic dodecahedron. So let's now we're going to define the kinds of domains that we can look at. So we're going to look at domains in this hyperplane where the sum of the coordinates is 0, which are relatively open. So they're open as subsets of this hyperplane and star-shaped. Okay, so we'll say that A is symmetric if it is symmetric, if it's invariant under the Sn+1 action. So the symmetric group acts on, of course, on Rn+1 by just exchanging the coordinates. So we'll say that our set is symmetric here. So it's not, this is not the origin symmetric, it's another symmetry condition. Okay, so this is symmetric. And a stronger condition is what we're calling balanced. So we say that A is balanced if A is symmetric, and for every point inside of A, if you take all of the different permutations of the coordinates and you take the convex hull of that, that's contained in A. Okay, of course, this is weaker than being convex. But there are many examples of non-convex things that are also balanced. Okay, and so I also want to define this function rho, which does the following thing. So if I take a point in Rn+1, what it does is you look at the ordering of the coordinates, and then you take the difference of the two consecutive ones. So I take my P, my vector P, I put the coordinates in decreasing order or in non-increasing order, and then I take the difference of two consecutive ones. So that's going to be a map that goes from Rn+1 to Rn, but all the coordinates are non-negative. So it actually takes values in the first orthant of Rn. Okay, so that's my map rho. And one thing that you can notice is that if you have a symmetric set, then A is determined by its image by rho. Okay, that's again a simple exercise. Okay, so what we can prove is for every symmetric set that the Lagrangian product of that particular simplex and A is symplectically equivalent to a toric domain. So that means that we can embed our Lagrangian product up to 1 minus epsilon into the toric domain, into a toric domain, and then we can embed that toric domain into 1 plus epsilon times this product. Okay, and the toric domain is determined basically by the image of A by the function rho with a little factor, and the factor is n+1. Okay, so we can prove that for every symmetric set. And if A is balanced, so that stronger condition, then we actually have a symplectomorphism. Okay, so as a corollary of that, we can prove that the ball is symplectomorphic to the product of the simplex and this Rn. And the proof, if we believe the theorem, the proof is very simple. The proof just has 2 little steps. The first one is to note that Rn is balanced. That's just because it's convex, so it is balanced. And now we see that if we take a point in the image of P by rho, then the sum of the coordinates of the image is going to be equal to this parabolic sum. So it's the sum of two consecutive coordinates. So that's just going to be the maximum, the largest coordinate minus the minimum coordinate. So basically, if you want that the sum of the coordinates of the moment map is less than a constant, that's the same as requiring that the maximum coordinate of P minus the minimum coordinate of P is less than a constant. So yeah, so remember Rn was just the set of points in that hyperplane where this difference here is less than 1. Okay? So yeah, so that's the corollary. Okay, any questions about this?
Maybe it's a silly question. I'm still trying to kind of process the kind of how rho looks.
Yeah.
But can you use this theorem to show, to give new examples for toric domains that are symplectomorphic to convex domains, but it's not clear that they are from the toric image? You know what I mean? So like,
definitely. I mean, you can draw a lot of things. I mean, basically,
okay,
draw anything in the moment map that's reasonable, like say star-shaped, and that will give rise to a symmetric A. And if you're a little careful, that will give rise to a balanced A. And then basically anything that whose pre-image by rho is convex will give rise to a balanced A, and then we'll have a symplectomorphism. And you have even more like symplectic equivalences. So yeah, it just gives rise to a huge family of things. So let me actually show you some nice examples. So so here, if you look at, I'm actually doing kind of the inverse engineering now. So like I start with my favorite toric domain, say an ellipsoid, and I can look at what A will give rise to the ellipsoid. So for which domains A is the symplectic, is a toric domain that we obtain the ellipsoid. And here's a picture of what happens for the A. So it's actually kind of surprising, but so this is always going to be a hexagon unless B is equal to 2A or A equals to 2B. But supposing that A is less than B. So for B equals to 2A, we have a degenerate hexagon, so a triangle. And for B less than 2A, we have a acute hexagon. And for B bigger than 2A, we have like an obtuse hexagon. And it's not hard to check that actually for B bigger than 2A, this is not balanced. So basically our theorem will imply that we have, we know that we have a symplectomorphism for, in the case where B is less than 2A, but when B is bigger than 2A, we only know that we have a symplectic equivalence. Okay, so this is a big class of new examples. And now, of course, after you look at the ellipsoid, the next thing you look at is the polydisc. So here's the polydisc. I mean, these are just two examples, but the polydisc will always look kind of similar. So we just drew the picture of P11 and P13, but it's always this kind of thing, and it's never actually convex. The A is never convex, so actually A will never be balanced, but still we have interesting symplectic equivalences. And we don't prove that the symplectic, that we don't have symplectomorphism, just that our technique for going from symplectic equivalence to symplectomorphism doesn't work. Okay, so these are examples. So before I get into the proof of this, and just before I tell you where the total lattice comes in, let me tell you about related results, which I've been calling some toric domains in disguise. So this is kind of maybe a history of this subfield, at least from my perspective. So here are some toric domains that are hiding in nature, but we can look hard for them and we can find them. So the first one is the Lagrangian by disk itself. So that's one of the first Lagrangian products that you look at, maybe the first one, because that's the one that's related to billiards in a disk. And I proved, and it was published in 2017, that this is symplectomorphic to a concave toric domain. So it's the first one that I discovered, and this is actually interesting because this concave toric domain is bounded by a smooth curve, which is something that doesn't happen very much in the toric world. But it's not a problem because this is not a closed manifold. And then Jahan and I generalize this result to a LP sum of two disks. So instead of taking the product, you can approximate the product, for example, or you can just take the LP sum of two disks, and that's always a simplex toric domain. And it's interesting, of course, as P goes to infinity, this LP sum converges to the product, the infinity sum, which is the product. So, but you can look at the whole family for all P's from 1 to infinity. For P equals 2, you have the ball. And for every P greater than 2, you still have a concave toric domain. And for P between 1 and 2, we actually have a convex toric domain. So yeah, it's interesting to look at that. And in our paper, we look at, Gromov widths and embeddings into balls. So you can look at that if you're interested in that. Another recent example is if you look at the unit disk bundle of a hemisphere, that's symplectomorphic to a ball. So this result was also published last year and uses kind of similar techniques, but I also think it's a little bit surprising. Although I think it was known in some other ways that the Gromov width was 2 pi, but we can actually prove the symplectomorphism of the disk bundle of the hemisphere. And in fact, we can go all the way to everything up to 1 point. So if you remove 1 point from your sphere, the disk bundle is symplectomorphic to a symplectic polydisk. So what's known as P 2 pi 2 pi. And ignore the respectively. I think that's a typo. And more recently, with Brian and Alejandro, we proved that you can do that for an ellipsoid too. So like a two-dimensional shell of an ellipsoid in R3. If you remove the North Pole and you look at the disk bundle, that's symplectomorphic to a toric domain. And as you vary A, the toric domain would have different properties. So for example, for A greater than 1, this is going to be what's called a weakly convex toric domain. And for A less than 1, so this is that's what's called the oblate ellipsoid. And for the prolate ellipsoid, which is when A is less than 1, it's a toric domain that's neither convex nor concave. And finally, the last example that I want to mention is that before with the Sepe, we did something similar, but instead of looking at the hypercube, at the simplex, we looked at the hypercube, and this is a lot simpler. This is a lot easier. So we proved that the Lagrangian product, the hypercube, and a balanced region in Rn, but the balancing condition is different. That's also a toric domain. Okay, so that's the older story. So now I'd like to move on to the proof of the main theorem. But before that, are there any questions? Okay. So the proof uses what's called the Toda Lattice. So the Toda Lattice is a Hamiltonian system given by this Hamiltonian here. So this Hamiltonian, it appears naturally in physics when you're trying to study, I think, crystals and how particles. So this is basically the movement of a system. This is a system of n+1 particles that are interacting exponentially. So as two particles get closer, they have they repel, basically. That's what the system gives you. So here's the actual Hamiltonian system. So why does this have anything to do with our situation? One way to see it is by looking at a deformation of the Toda Lattice. So you can deform the Toda Lattice like this. So you multiply the q coordinates by c, and then you multiply the whole thing by e to the minus c. And you note that as c goes to infinity, this potential, this h, is converging to the following function. So if qi minus qi plus 1 is always less than 1, this converges to 0. And if qi minus qi plus 1 is bigger than or equal to 1, this converges to infinity. So what this means is that the flow of this Hamiltonian vector field is convergent to a billiard flow. So the norm of P, it's convergent to a billiard flow in this subset. And apologize, it should be n+1 here. So of course, this subset is not it's not quite the simplex, but if you take any slice where the sum of the QIs is equal to 0, then you have a simplex. And it's not hard to see that this is preserved, that this equation is preserved by the flow. So the flow is actually contained in these hyperplanes. So we can just take one section and we're going to have our simplex. So this Hamiltonian is giving you the billiard flow in a simplex. That's why this comes up in our result. Okay, so let's go back to the total lattice and let's talk about the fact that it's integrable. So the total lattice actually is one of the reasons it's so interesting is because it was the first example of a nonlinear integrable system. So let me explain why this is an integrable system. Now, the first thing you can see is that you can change coordinates like this using this Flashka transformation. So you call AI this exponential, and then BI minus PI, or maybe PI if you want, but traditionally it was minus PI. And then now we have a new Hamiltonian system, which is quadratic. So it's much simpler. Of course, the Poisson structure has changed. It's actually not even a symplectic transformation, but it's a Poisson transformation. But we can still write down what the Hamiltonian system is. Okay, so you can just change coordinates if you want and write it like this, or you can use the Poisson formalism and see how the Poisson bracket changes. And then you still have a Hamiltonian vector field for this new H. And that's what the system is. And what's so nice about the system is that there is a so-called Lax pair for it, which means that there are two matrices, L and B, such that the Hamiltonian system is equivalent to this ODE here. L dot equals the Lie bracket of L and B, where L is a symmetric matrix. And it doesn't matter what B is. I mean, B is an anti-symmetric matrix at which I won't write down. But L is this very nice matrix, is relatively sparse. It's a tridiagonal matrix with these two extra entries at the corners. Okay, so one simple fact from the Lax pair, observation is that if you have such a pair, then the spectrum of L is going to be preserved by the flow of the system. Okay, so this is a very simple calculation, a basic spectral theory. And in fact, Edon proved in 1973 that the total lattice is completely integrable. This is not obvious from the spectrum, but it is true that the spectrum, if you look at, for example, the coefficients of the characteristic polynomial, that they're all independent. That's what it means to be completely integrable. You have these quantities that are preserved by the Hamiltonian flow, and these quantities are independent of each other. Okay, so if the system is integrable, then we can apply sort of the basics of integrable systems, of which I think the most basic thing is what's called the Arnaud-Levier theorem. So this is something that is quite classical, but I think it's not that well known in symplectic topology. I don't know if we kind of forgot. We forget to teach people about that. We only teach them about homomorphic curves and floor homology, but it's something that some people used to know, and I think it's a little bit less well known. So let me tell you about the Arnaud-Levier theorem. And I apologize to the people who think this is, old math. So it's the following thing. So if you take a symplectic manifold and we consider n Hamiltonians on it, and my manifold is 2n dimensional, and such that the Hamiltonians commute. So that they Poisson commute, or, in other words, their Hamiltonian flows commute. So if you take a regular value of f, such that the pre-image is compact and connected, then the first thing is that the pre-image of C will be diffeomorphic to a torus. So by the way, someone asked me, how can Arnaud and Gouville have collaborated? Because I don't think they were alive in the same period of time. So, of course they didn't collaborate. I think this is just a result in Arnaud's book that he quotes, that he says it's due to Leuville, but I think that, it's not that clear in Leuville's work, or it wasn't stated like this in Leuville's work, but I guess he attributes that to Leuville somehow. But I think people usually, in integrable systems, they call it the Arnaud-Leuville theorem. Anyway, so the first fact is that if you take a completely integrable system, so you have n integrals in a 2n dimensional symplectic manifold, and you take a regular value such that the pre-image is compact and connected, then the pre-image has to be diffeomorphic to a torus. So it can't be anything else. And moreover, it's basically locally a Lagrangian, a toric Lagrangian fibration, a Lagrangian toric fibration. And you can actually extend it quite a bit. So here's the way I'm going to extend it. So if you take an open set in M, such that the image by F is simply connected and does not contain any critical values, then you can actually extend this diffeomorphism to a symplectomorphism to basically a symplectomorphism of a toric domain, to a toric domain, or to a Lagrangian toric fibration if you prefer. So here's the statement. So there exists a diffeomorphism of the image of U and a symplectomorphism of the top, such that this diagram commutes. So this is a toric domain, like I defined, and this mu is the standard moment map. So what that's saying is that on quite a large subset, this domain is actually just a little piece of a toric domain. So someone said this is what physicists call action angle. That's right, Josh. This is exactly what the physicists call action angle. So here's the action coordinates. So you can actually compute this map phi, and it can be computed like this. So phi is so first you choose n curves, gamma 1 to gamma n, which generate the first homology of this torus over the so the torus that's over the fiber over the C. So you choose these n circles, and then you integrate a primitive of omega. Okay, so a primitive will exist locally, and if your set is large enough, then it'll still exist. I mean, in our case, we're going to be in R2n, so you can always take a primitive. So this is what's called the action coordinates, and the angle coordinates are basically a dual set of coordinates, and it's part of the theorem. So you can think of it like you can think of the theorem kind of like this: define these action coordinates. So define this phi. So for an appropriate set, this phi will give you a diffeomorphism. And you can lift this to a symplectomorphism, or in other words, you can find a dual set of coordinates, which are called the angle coordinates, which all close up, so that this is actually going to be a symplectomorphism. Okay, that's another perspective. But what really interests us is the way that the theorem is stated like this, and basically that what this is saying is that U is a toric domain, and the image of the moment map is given by the composition of F with phi. So what we really want to do is understand the image of phi, because that's going to give us the image of the moment map of the toric domain. And
who is the omega? Sorry.
What?
Who is omega?
It's just the image of phi. So there exists an omega,
Mm-hmm.
and we don't know it at first what it is. But it's
do I have some
subset of Rn that's given that's the image of this. Yeah.
Can I choose phi?
Not exactly. I mean, you have to. I mean, using this theorem, you have to integrate a primitive of the symplectic form over a set of circles.
Oh, I see.
So, I mean, there are lots of things you can do, and in fact, if you just do any kind of set of circles, you might not even fall into the first orthant of Rn.
Mm-hmm.
That's quite possible. So the theorem wouldn't, doesn't mean that you can do that for even any set of curves like this. But you can always modify it so that you fall in the first quadrant of Rn, in the first orthant of Rn. And this actually makes sense. I mean, if you want to basically do anything, you could, instead of taking the standard moment map, you could take like omega times Tn, like the Lagrangian product of omega times Tn, and then the projection to the first coordinate. And then it would be true for a wider set of phis. Yeah. But
Thanks.
one little detail that I'm just going to say, but I won't write down details, I won't write anything down, is that you have to regularize over the critical values. So that's something that people in integrable systems are used to doing, and we have to do it, but I won't really talk about it. Okay, so once we know it, we need a little bit of spectral theory of the total lattice. So one thing to know is that if you look at the eigenvalue problem of that matrix L, that tridiagonal matrix with the extra terms, this is equivalent to looking at this this gives rise to this difference equation. And in fact, you have an eigenvalue for L if and only if this equation has a non-zero solution y, which is periodic. Okay, so that difference equation is related to L. And then now we look at a solution to this to this difference equation with initial conditions y0 equals 1 and y1 equals 0. And that gives rise to yk of lambda, so which is going to be a polynomial of degree k plus -2. And this is not actually an eigenvector it doesn't correspond to an eigenvector of L because this is usually not symmetric. I'm sorry, not periodic. Okay, that's a little detail for the experts. But now, we can, if we're given this polynomial, which is one of the fundamental solutions, then we can look at the roots of the n plus 2 and k equals n plus 2 that will be a polynomial of degree n, which has n roots. We can show they're all real numbers. That's not completely obvious, but it's true. And then we can look at this fi, which is minus log of the polynomial with k equals n minus 1 evaluated at μi. And the theorem by these people, it's actually apparently due to Moser, but it was written down in Viterbo in the early 70s. And Flashka McLaughlin just say that it's probably true, but they don't bother to do the calculation. But anyway, it's not so simple, but it's basically similar to the KDV case, which is an infinite dimensional version of this, is that the map that for Q and P spits out F, the numbers F and the numbers mu, this map is a symplectomorphism. So once you know that that's true, then now you can apply action angle coordinates. So it goes like this. So you look at the discriminant of the difference equation from the previous slide, which is basically a polynomial that has the property that if lambda is an eigenvalue of L, then this polynomial evaluated at lambda equals 2. So it basically is what tells you that there exists. It's a polynomial on lambda that will tell you that the difference equation has a periodic, an periodic solution. And Viterbo showed the following thing. So if now you look at the roots of, this should be capital D squared equals -4. So the roots D equals when D equals 2 and when D equals -2, then that mu I that I defined in the previous slide is always between lambda 2i and lambda 2i plus 1. And moreover, this fi is some inverse hyperbolic trig function with this D. So what that means is basically the mu is going this interval and the fi is either plus something or minus something. So here, if you're a little careful, you see the circle that you need to take to get your action coordinate. So now we can use the Arnold-Liouville theorem and we get these action coordinates, which will basically just be the integral from lambda 2i to lambda 2i plus 1 of this inverse hyperbolic function. Of course, there's several steps that I'm skipping, but I want to just show you the expression of the action coordinates. And they will induce symplectomorphism by, the Arnold-Liouville theorem plus regularization theorems. And finally, what we need to do now is we need to do that for deformation of the total lattice. So that was the action angle coordinates for the total lattice. So now you deform the total lattice, using this parameter C, and then you can look at the action function. And the thing is that the action function, if you remember the matrix L, it had B's along the diagonal, it had a bunch of other A's. So as C goes to infinity, all these A's are going to go to 0, and we're going to have a diagonal matrix. And the eigenvalues are just going to be, the coordinates of P. And let me just go back to this expression. When the C goes to infinity, the integrand is going to converge to a constant. It's actually going to converge to n plus 1 over 2. Which is why this action function will now just converge to a constant, which is n plus 1 times the difference of these P's. Because the eigenvalues will be just the P's, the coordinates of P, put in order. So that's how we get the action function. So that means that this phi infinity of QP is just that function rho of P that I had defined earlier. And that's basically all we need. So there is a technical thing, which is that when A is just symmetric, we can't quite get the whole symplectomorphism, but we get the symplectic equivalence. And when A is balanced, then we can actually find an exhausting family of symplectic embeddings, which will give rise to the symplectomorphism that we want. And I just want to finish with two open questions, which is, instead of just looking at the rhombic dodecahedron, we can look at other polytopes. So is it true? Is it possible that the product of simplex and other polytopes is symplectomorphic to a ball? And the answer should be yes. So in dimension 3, for example, there we have these 5 candidates, and we believe they're all that there exists a simplex such that the product of with each one of these is going to be symplectomorphic to a ball, although we haven't quite proven that. And the second question is, do other root systems, so it's well known that the Toda Lattice is related to the root system AN. So what about other root systems? Do they also give rise to interesting symplectomorphisms? And I think the answer is to this question is yes and no, but I'm happy to discuss that more if anybody is interested in it. Okay, so thank you.
Thank you, Vinny. Beautiful talk. Any questions?
Yes, we want to hear more about the root systems.
Oh, okay. Okay, so let me just say that this is work in progress, and I think that the answer is yes and no, because if you change the root systems, basically, then you have a generalized Toda Lattice. So you have to change. You can change the potential to have a Hamiltonian system that's related to the particular root system that you're talking about. And you can probably do action angle coordinates, although it has not, I don't think it has been done very much in the literature. And I think you can deform it in the same way and you can get products, but I think that somehow they're going to be less interesting. So I think sort of the AN root system will give you the most interesting or the most generic product. And I think that the other ones will be the generations of the one that we have. I mean, I think, for example, if you take A1 times A1 times A, like the product of several A1s, then we actually get the symplectomorphism that I had with Sepe in 2019. So with the hypercube. So actually, this is the first Fedorov polyhedra. So we already know this one. And I think that, you know, this just based on what I tried to look for the other ones, we will get some of the some degenerations of that. And I should say the one thing that is still quite mysterious to us is why we get the rhombic dodecahedron, which is this guy here, the second to last, and not the permutahedron, which is the last one. The permutahedron really should be the thing that's the most general, the most generic of these polytopes. But somehow we only get the rhombic dodecahedron, which is already a degeneration of it. Maybe it is possible to generalize, to use the AN. So actually right now, I think the answer is, to question 2 is we don't get interesting symplectomorphisms, but we get other symplectomorphisms. But we should be able to, I think, we might be able to extract more interesting symplectomorphisms already from AN. But I still don't know how.
Oh, thank you.
There's a question in the chat. Is Viterbo conjecture for the product of Lagrangian disks implied by the existence of a symplectic embedding of capacity 4? I ask this instruction. I think that's true, Philip. I will look at the preprint after the talk, but I think that the answer to a question should be yes.
I wanted to ask how being balanced helps.
Yeah.
Or
so what happens is, you know, so we can use, let me go back here. Yeah. So we use the Arnold-Liouville theorem and integrable systems techniques to get a symplectomorphism of something to something. And the something that we get, the two things are not the Lagrangian product, but it's something that is an approximation of the Lagrangian product. So, you know, it's some thing with smooth boundary. So we show that this subset with smooth boundary is symplectomorphic to a toric domain. And the toric domain, of course, is not quite the limiting toric domain. So we have to do a limiting argument to like fill in this, this Lagrangian product, and that will fill in the toric domain. But so that's the sensitive thing. And I mean, you can go back to like, you know, Schlenk's embedding things or Trainer's embeddings from like the 90s. And for example, if you look at the simplest example of Lagrangian products and balls is the square and the diamond. So that, you know, goes back to Felix's book, and you can do that in every dimension actually. And you can find an explicit embedding from a little, from a smoothing of that into the ball and vice versa. And you can find a family of embeddings basically that fill both sides. But the question is, so that will give you basically the symplectic equivalence. So we can do that for every symmetric. But then the question is, how can you glue these to obtain a symplectomorphism of the interiors? And that's very subtle. So in the case that I alluded to, in that Schlenk had constructed these embeddings, you can do that in dimension 4 using a highly sophisticated technique by Macduff, you know, like basically that, you know, that uses the fact that the isotopy of embeddings of balls. So that uses, you know, the Gromov, the Cyber-Witten variant and all that kind of stuff, the technology that she developed in the 90s for symplectic embeddings. So you can do that to prove basically that the square times the diamond is symplectomorphic to a ball. You can use that, for example, to in Cristofaro Gardner's theorem that concave toric domains embed into convex toric domains, if and only if the symplectic capacities don't obstruct. You also use that because you can use that embeddings of concave toric domains are also have this flexibility. But we don't know that in general. So that's why we can't in general say if you have embeddings that are filling, then that we can isotope them in a way that make the embeddings kind of exhaust the domain, and you have a symplectomorphism of the interiors. So we need an extra condition. I mean, maybe it's true.
Yeah, that I understand, but I couldn't figure out why the balance, like being balanced, saves you.
Yeah. So the being balanced is the condition that you need to show that the domains that you have in that converge to the Lagrangian product are contained in each other.
Oh, I see. Okay.
So as C goes to infinity, we have these natural domains that are going to be inside of the Lagrangian product, and they could be converging, but in a non-exhausting way, you know. And that's what happens, for example, like, you know, if A is concave, that they will converge, but usually not in a exhausting way. But if it's balanced, then we can prove that they will converge in an exhausting way, and that we get the symplectomorphism.
Thank you.
I think there are some more questions on the chat. Josh said, I think maybe some Greek mathematical ecologists wrote action angles, at least lax pairs for B and C in the end, because they found less ecology was used. Oh, thanks, Josh. I'll look into that. That's helpful. You know, I've kind of gotten, I've had to look at a lot of physics papers, and I hadn't really had to do that before this kind of work, and they write very differently. But, you know, if it's a mathematical ecologist, I don't know if I would have come across it. And I don't actually know what that means exactly, but yeah. And Egger said, let K be the unit ball, then the cylindrical capacity of this K times K is also 4 by projection. Oh, okay, yeah, that's right. Thanks, Egor. Yeah. So yeah, just for the unit ball, it's not so hard to compute the cylindrical capacity, but not the Gromov width, right?
Right, and the Gromov width is then computed by Philippe.
Yeah. Great. Well, thanks everybody for the comments and the questions.
Any more questions? If not, that we can thank Vini again.